Welcome to the Explainer. Have you ever stopped to think about how a simple on-off switch can power literally everything? Your phone, the internet, all of it? Well, today we're going to decode the secret language of computers, the fundamental rules that build our entire complex digital world from the ground up.
Okay, so to get this, you first need to understand signals. You've got analog signals, which are smooth, continuous. Think of a sound wave. They have infinite little variations. But digital signals, wow, they were the real game changer. They're built on this wild idea. A signal can only be in one of two states, all the way on or all the way off. There is absolutely no in-between.
So why did this simple on and off system completely take over? Well, it's all about efficiency. Digital signals can cram billions of these on and off states into every single second, making them insanely dense with information. They're way easier to store and process. But here's the real magic: perfect copies. You can copy a digital file 1,000,000 times, and that millionth copy, it's going to be absolutely identical to the first. That's something analog could never, ever do.
So if digital is a language, what are its letters? What's its alphabet? Well, it all boils down to one incredibly simple, yet ridiculously powerful idea.
Meet the bit. The name's short for binary digit, and it is the absolute smallest piece of information a computer can possibly handle. That's all it is, a single choice between two options. We just happen to represent them with the numbers 1 and 0. That's it.
And it's honestly kinda staggering how simple this is. Just think about it for a second. Every single thing your computer does, from the most complex video games to cutting-edge AI, is built on this one idea: a light switch. When that switch is on, we call it a 1. When it's off, we call it a 0. This is the fundamental building block for everything that comes next.
So if one bit is like a single letter, how do we start to form words and numbers? Well, it's easy. We just string those bits together. And this is what allows computers to count, just in a way that's a little different from how we do it.
The best way to wrap your head around this is with a fantastic analogy: a car's odometer. In our cars, right, each little wheel has 10 digits, 0 through 9. When a wheel gets to 9 and you go one more mile, it flips back to 0 and clicks the next wheel over. Easy enough. Now just imagine a binary odometer. Each wheel only has 2 digits, 0 and 1. So what happens when a wheel hits 1? Same exact principle. It flips back to 0 and clicks the next wheel over.
And you can see exactly how this works right here. To go from 1 to 2, that first wheel flips from 1 back to 0, and that clicks the second wheel over to 1. Then to get to 4, you get a cool chain reaction. The first wheel flips the second, and the second wheel flips the third. By just combining these simple little flips, we can represent any number you can possibly imagine.
But let's be real, counting is just the beginning. The real power here isn't just representing numbers. It's using those numbers to follow instructions and make decisions. This is where the computer really starts to think. And to make those decisions, computers use a special kind of grammar. It's a set of unbelievably simple rules that are processed by these little things called logic gates.
Each logic gate is like a tiny bouncer at a club. It looks at the bits coming in, we call those the inputs, and based on one very specific rule, it produces a single bit going out, the output. It makes a yes or no, a 1 or a 0 decision.
Let's start with the strictest gate of them all, the AND gate. Its rule is super simple. It will only output a 1 if the first input and the second input are both 1. If it's anything less than that, the output is a 0. No exceptions. Its truth table here makes this crystal clear. Just look at that output column. See that? There is only one single row where the output is a 1, and that's the one where both input A and input B are 1. In every other case, the answer is 0 or false. A great way to remember this one is the movie analogy. If you tell yourself, I'm only going to the movies if I have a ticket and I have popcorn, well, you need both things to be true. If you're missing either one of them, you're not going. That's the AND gate. Next up, we've got the OR gate, and this one is way more laid back. The OR gate will output a 1 if input A is 1 or if input B is 1. And hey, if both of them are 1, that works too. It's much, much easier to please. And its truth table shows this perfectly. The only time you ever get a 0 on the output is when both inputs are 0. In every other situation, as long as there's at least one 1 coming in, you're going to get a 1 coming out.
This is just like paying for coffee, right? You can use cash, or you can use a credit card. As long as you have one of them, the transaction is a success. You get your coffee.
That's the OR gate.
And finally, the simplest of them all, the NOT gate. This one's only got one input and one output. I call it the opposite day gate. If you put a 1 in, you get a 0 out. If you put a 0 in, you get a 1 out. It just flips the signal. That's all it does.
Okay, now this is where it all gets truly mind-blowing. We've talked about counting with bits and 3 simple logic gates, AND, OR, and NOT. And that is it. That is literally all you need to build any computer that has ever existed.
By linking these simple little gates together in all kinds of clever combinations, we create circuits that can do anything. They can add numbers, they can store memory, they can follow the instructions of a program. It's how these simple rules become the recipes for achieving unbelievably complex goals.
And that's really the beautiful secret at the very heart of all our technology. It's not magic. It's just the result of combining billions of simple, predictable rules to create behavior that is so complex that it feels like magic. And all of it, every last bit, is built from that single on-off switch.
So that's the fundamental language of computers. And it leaves us with a really fascinating question to chew on. If today's entire world was built on this one simple idea of on and off, what's the next simple idea out there that could change everything all over again? Thanks for joining us on The Explainer.